Starting recording. Cool. Okay, so yeah, last time we were talking about, we basically ended up talking about the paramagnet. So today we're gonna be done with discussing our relationship between temperature and entropy, and we're going to move on to discussing the relationship between pressure and entropy. So we're going to title this Mechanical Equilibrium and Pressure. And we'll do basically the same thing that we did for temperature, but now we're going to do it for pressure. So previously, yeah, we considered systems that mainly just exchange energy. And that's correlated with the thermodynamic quantity that we think of as the temperature. But now what we want to consider is the exchange of volumes. So consider systems that can actually exchange volume now, where before we had just fixed it to be a constant. Gluten-free brownies. I'm not gluten intolerant to anything, so I never go for any gluten-free stuff personally. Okay. So yeah, I mean, in the past we've discussed how the entropy we think should scale with the volume. So if you make the space bigger, there are more microstates available to whatever you're talking about. So we should expect some kind of relationship between pressure and entropy. And so previously when we were talking about stuff like this, what we did was we considered the entropy as a function of the energy in like one part of a two-part system. We'll say we've got A and B and we're looking at just A. And we always saw some kind of, feature that looked like a Gaussian, right? We've beaten this to death. You had to show it on the exam. We've talked about it in class, like talked about this tons. So like in here is kind of the region of like thermal equilibrium. So now what we're going to do is we're going to take this, and rather than just considering letting energy exchange, we're going to let volume exchange now too. So what do we think this should look like? So if we have now, let's say, a two-system system as well, we've got UA, and we've got a volume corresponding to system A, and we've got entropy plot over here. What do we think this should look like for an interacting system? So use this as an analogy. So when we only let the energy flow, we saw something that looked like a Gaussian just in this two-dimensional graph. But now, what should you expect? Any thoughts here? Straightforward generalization of this. It should just be a two-dimensional Gaussian. And I'm not going to try actually drawing it here, but I went in Mathematica and just made myself a quick little two-dimensional Gaussian that I wanted to pop up real quick. So we should expect that it will look something like this, right? So we've got temperature along one axis and pressure along another. We should expect that if we look at either of them just as like a two-dimensional surface, we'll see a Gaussian there, if this is entropy. And if we turn it and we look at just temperature, we see what we saw previously, which is just another Gaussian there. So now we've just got a two-dimensional Gaussian. Nothing too crazy there. How do I get out? Get me out of here. There. Okay, so won't draw, cite Mathematica. All right, so what does equilibrium mean now? Well, it's going to mean that if we take the total entropy and we take the derivative with respect to the energy of system A, just like before, that is going to be 0. But now since we're letting volume exchange, we're also going to include this extra one, which is just the analogous condition, but for the volume of system A. So this is what equilibrium means in our current thinking. Okay, so we used this previously to relate to temperature, right? Now what we're going to do is we're going to try to do an analogous thing. We're going to relate this to the pressure. So we'll do exactly what we did before. We'll just take S total, take the derivative with respect to A, break it up. We know that entropy is additive, so it's just SA plus SB. We've got a two-part system that's interacting. So del SA over del VA plus del SB over del VA. And we know what? Well, how can we relate VA to VB? So if we want to get this as like del SB over del SB, or del VB, anybody have any ideas how we would do that? So analogous to the total energy being conserved. So like previously we said that like U total is equal to UA plus UB, and obviously that's conserved. So if we take the differential of the total U, and I'll leave off the total now, that this was just DUA plus DUB, right? But that should be 0 because this is conserved. So DUA is just minus DUB. And so just like that, we also are going to have that the total volume is conserved, and it's also just additive. So therefore, we just have the same relationship. So it's just going to be minus the other one. So if we write this, we'll have del SA, del VA, minus del SB over del VB. Okay. So then we can just say that at equilibrium, we can just rewrite the condition as being the following. So at equilibrium, this is the thing that is the same between the systems if they're exchanging their volumes, basically. And so this is exactly the same thing that we did for the energy before. But now what we want to do is we want to relate this quantity in some way, shape, or form to the pressure, just like we did for temperature. So like in the terms of, this kind of looks like a U, sorry. Those are all V's. So like we did for temperature, we looked at this and said, oh, this is the thing that's the same for the system when it's at equilibrium. How can we relate that quantity to the temperature? And then we looked at its units and we concluded that it's just related inversely because it has the inverse units of temperature. So now we want to do the same thing and relate P, the pressure, to del S over del V. So let's look at some units. So we have that the pressure just has units of what? It's newtons per meter squared, right? And what about the units of del S over del V? Can anybody give me that? What are the units of entropy? Anybody remember? So entropy, I'm seeing some chats fly in. Here we go. Okay, yeah, so entropy. Yeah, it's not Kelvin over Kelvin. That was a typo. So entropy has units of joules per Kelvin, right? And volume has units of meters cubed. So we'll multiply by 1 over meters cubed. And we'll write joules in terms of newtons times meters. So if we do that, we just have that this is an SI units, meters squared times Kelvin, right? So at this point in time, you're starting to see potentially how you would get this quantity to be related to the pressure, because we see a Newton per meter squared here, but we also see that we have units of Kelvin right here. So what we're going to do is we are going to postulate the following. Well, let's just look at it first. So yeah, obviously, if we wanted to get the right units, you would just take a temperature and multiply this, and you would get something that looks like a pressure. So what we'll do is we will postulate that the pressure is equal to the temperature times the derivative of S with respect to the derivative of V, U, and N held constant. Okay, So now let's think about whether this actually makes any sense or not intuitively. Hope everybody got that. Okay. So let's look at it. So if we have that del S over del V is large, then according to that expression, it tells us that P is large and vice versa. So basically what happens here, so think of this is if the system gains a lot of entropy from small delta V, then the pressure is really, really large. So system lot of S from small delta V. So basically, if this is really large, just changing the volume a little bit will change the entropy by a bunch, which corresponds to the pressure being really, really large, which just means that the system is readily willing to expand, right? So this is analogous to when we were talking about spontaneous transfer of energy as well. So if this was a U, then this thing, well, it's inversely related, but if the slope of the entropy versus the energy was really, really large, then it was really, really willing to accept energy in order to increase its entropy, right? So vice versa, now we're just substituting temperature for volume. Okay, now let's make sure this equation is consistent with previous stuff. So just like we did before. So let us recall that for an ideal gas, we had that the microstate looked like, or the multiplicity function, looked like some function of n times v to the n times u to the 3n over 2. And so if we want to calculate the entropy from this, you just take S equals k ln of omega. That's equal to n times k times ln of v plus 3/2 n k ln of u plus k times ln of f of n, whatever that function is. It's just encapsulating all the stuff that we don't want to write out fully. So let's calculate the pressure. So according to our postulation previously, we said that the pressure should be the temperature times the derivative with respect to S, with respect to V, U and N. That is T times NK, del over del V of log of V, just on that first term. And then the other terms don't depend on the volume at all, so those just go away. So you've got some plus zeros there. And the derivative of the log is just 1 over whatever that thing is, right? So this is just P equals T times NK all over V, right? But, well, what does this tell us? It just tells us that PV is equal to N times K times T, which is just the ideal gas law. So we see that if we take our assumption for the form of P as it relates to the entropy as a function of volume, and then we just use our result from previous microstate counting, we just get the ideal gas law back. So it seems like this definition is working properly. Okay, so we'll take that to be a quote-unquote proof of this. Seems to confirm what we think for some basic stuff like an ideal gas. Now what we're going to do is we're going to derive the so-called thermodynamic quantity, at least for varying U and V. We'll derive it again when we also let the number of particles move around as well. So the thermodynamic identity. So, okay. Yeah. What's your question, Saif? That's a good question, which we are actually going to answer right on the next slide. Okay. So just hold that for a second. And if I don't answer it in the next 2 minutes, just shout at me. Okay. So yeah, we're gonna understand how the changing entropy relates to the potential compression, or how it doesn't relate to it. And what we'll actually find is that you can just forget about the compression and only concern yourself with the heat and the temperature. So we'll show that now. So what we're going to do is we consider a system, and we're just going to change U and V by small amounts. Delta U and delta V. And we're going to ask ourselves, if we do that, what is delta S? Okay, so the way we're going to actually do this is we're going to do it in 2 parts. We'll do one step where we take U to U plus delta V, or sorry, U plus delta U. And then step 2, we'll take the volume and take it to itself plus a small change, delta V. So now we're going to ask ourselves, well, how does the entropy change? So we'll have delta S from the first part plus the delta S from the second part. And now we'll do a little trick in physics that you should just commit to memory, and it's the simplest dang thing that you've ever seen in the world, but it comes up everywhere in many shapes and forms. We're just going to multiply by 1 in a special way. Yeah. What's the chat? Yeah, no worries. If anybody ever has to go early, just let me know and you can take off. But yeah, so yeah, this is just a small aside, but multiplying by 1 just comes up everywhere. I mean, in quantum field theory, thermodynamics, quantum mechanics, like electrodynamics, like you do this everywhere. So we're gonna hold V constant for the first part. So it will look like this. We're just multiplying by 1 here. And then we're going to multiply by 1 in a different way over here. Okay, so we've done nothing here except multiply by 1. And now we're just going to do a little bit of potentially illegal rearranging, but it works out. So we're just moving around symbols at this point. That's a V. U held constant, delta V. Okay, now we said they were small over here. Now we're just going to formally make them infinitesimal units. So now we're going to write this as ds is equal to del S over del U with V held constant. This is du plus del S del V with U held constant dV. Okay. Now, does anybody have any thoughts about how we could simplify this term and this term using thermodynamic quantities that we've derived recently? So we know that this is related to the temperature, right? So what is that? That's just 1 over the temperature, right? So that's 1 over T du plus, now what's this? We just postulated it on the previous page. Anybody? Quick. Think fast. Pressure? Close. It's not quite. It involves the pressure. What else? Think. Yeah, P over T. Good. Okay, pressure over temperature. Yes. Okay, so now we will just rearrange this a little bit. And we can get the following. So just multiplying by T and then moving the du onto one side by itself, because it likes to be alone. We derive the so-called thermodynamic identity for a system whose energy, entropy, and volume are allowed to vary. Okay, so this just relates the change in energy to the change in entropy times the temperature to the compression work that's done. And so do note that at least for this version of the thermodynamic identity, we assumed that del S, del N is just 0 the whole time. We didn't allow that to change. It was completely fixed. Okay, so we can use this now. You can just remember this formula, and you can quickly derive the other two that we've found that relate temperature to derivatives and pressure to derivatives. So if we say that like the volume doesn't change, if dV is equal to 0, then you just put that in there, and well, what do you get? You get that you can invert the temperature and invert the du, and so you just have that 1 over T is equal to del S, and I'm being sloppy with derivatives and partial derivatives, but that's just the way it goes here, guys. So, and this is with V held constant. So this is just the definition of temperature that we drove before. So that's one quick way to remember it. And likewise, if you hold U constant, you can show that TdS is equal to PdV, and then we can just say that P is equal to the temperature times the derivative with respect to V of U and N. So now you can basically just remember this one formula, and you can quickly and easily derive the two different relations between T and the derivatives and P and the derivatives. Okay? No questions there? Okay. So we are just about to answer your question, Safe. So now let's recall the first law of thermodynamics. Which at least everybody that I've graded so far seems to have recited correctly. So that's good. So it was that du, the exchange in energy, is equal to the heat added to the system, plus the work done on the system. So what can we notice now? Well, if we look back here, the thermodynamic identity looks very similar, right? So let's just take it and let's write it below it. So let's say that du is equal to TdS minus PdV. So now, if we assume that the only kind of work that takes place is like this kind of quasi-static compression work, quasi-static was the assumption that we used in like the first chapter when we assumed that this was the form of the work done. Well, then what we can do is we can relate this piece directly to the work and this piece directly to the heat. Okay, so if we only have quasi-static work done and the only type of work done that is done is compression work, then we can say that W is equal to minus PdV, which is just what we said before for quasi-static. So that's just what we said before. It's nothing new. But now we have the new thing, which is that Q, the heat added, is just going to be the temperature times the change in entropy ds. And so this is under the same assumption, so I'll also write quasi-static over here. Okay, so under these assumptions now, we see that the change in entropy doesn't actually depend on the work done anymore. The only things that you need to track if you want to find out what the entropy change is the temperature and the heat added. So let's just show this real quick. So we would have ds written in terms of that. It's just Q over T, which looks very similar to an expression that we derived before. So if, for example, we have an adiabatic process where Q is equal to 0, then ds is also equal to 0. And this type of process is now also, instead of being called adiabatic, it can be called isentropic because the entropy does not change. And so we had derived a similar result from this before. But we had said that we knew ds was equal to du over t. And previously we had to assume, because we only had the first law of thermodynamics, we had to assume that there was no work done on the system. And that was the only way we could write that this was Q over T. But now what we've shown, at least for the case that we're showing right here for quasi-static compression, that this equality right here actually holds up regardless of the intermediary. So the change in entropy is literally just the heat added over the temperature. So you can calculate it this way whenever you like. And so we could calculate it right now for a couple things if we wanted to. So I've got it calculated here for a liter of water. So if we want to calculate delta S, water. Okay, so let's take the water to be at T equals 100 degrees Celsius. And we're going to say that the heat added is 2260 kilojoules. Well, then to calculate the entropy, it's really easy. You just take one divided by the other. So we got 2260 kilojoules. I'm not going to do the conversion. I'll just write the answer. 60 joules per Kelvin. And then likewise, like we had done before, if you have that the temperature is actually changing, well, what do you need to do? You need to use the fact that Q is equal to, in this case, we're going to use the constant pressure form of the specific heat. It's going to be that the heat is equal to the specific heat at constant pressure times the differential of the temperature. And so if we want to calculate the change in entropy that way, we would just have to like integrate from some temperature to another temperature times that. And then if this is constant for most of this change right here, you can just pull it out and you just got log of the temperature. Okay. So did that answer your question there, Safe? Yes. Well, that's not, well, I mean, so what we did here was we actually did assume that both that all the things change. The energy can change, the entropy can change, and the volume can change. And so all we said was that if we also take the first law of thermodynamics, which has to hold, and the only type of work you have done is quasi-static compression, then this term gets totally absorbed there. And so this term has to be that Q right there. So, I mean, if pressure and volume are changing, it's exactly what we showed right here. It's that you only need to track the heat added and the temperature in order to calculate the change in energy and entropy. So you can... Mm-hmm. Yeah, you would... How would you get the heat? Like this. So you'd relate to the heat to like one of the specific heats, depending on whether you've got constant pressure or constant volume, times the differential with respect to T. And you would integrate instead of just dividing by Q over T if the temperature is changing. It's like we talked about previously when we were talking about this. I don't know if you remember. Does that help? That's right. Yeah, I see what you're saying. So I suppose here, yeah, you do probably have to assume that it's not going to change appreciably. That's a good question. I'll comment more on that later, but yeah, I think that the assumption is probably just that this doesn't change appreciably, that the pressure doesn't change appreciably to calculate that. Jacob, what's your question? Question part 2? Yeah, we had pulled that. Oh, I think that was. Let me flip through the book as well. That was a while ago. I think it might have been chapter 1. Yeah, I think it was in 1.6 when we talked about heat capacities. Yes. Yeah, basically 1.41. What's that? Which relation? This one? So this is only using the specific heat at constant pressure. So this is allowing the volume to change, I suppose. So yeah, I guess here we are assuming that the pressure is constant, but the volume can change. So that's why we're using the specific heat at constant pressure. Okie That is the def of heat capacity. Yes, this is essentially the definition of heat capacity. Just take off the P for the general definition of what heat capacity is. Okay, got about 6 minutes left. So let's see if we can get through diffusive equilibrium and the chemical potential now. So maybe you're seeing a trend at this point. We're basically just letting different thermodynamic quantities vary and trying to relate them to the derivative with respect to entropy in some way or another. So we did that for temperature, we did that for pressure now. Now we're going to do it for the chemical potential, which you'll see defined in a moment. So we'll call this diffusive equilibrium and the chemical potential. All right, so before we had, if we just let the energy vary, we had something that looks like this. Just a Gaussian in 1D, or 2D, I guess. And then we had this. If we let the volume change, I'm not going to try. A 2D Gaussian, what does it look like now? Anybody? It's kind of a trick question. It's going to look like a 3-dimensional Gaussian, so it'll actually be in 4 dimensions. So I don't know how the hell you're going to picture it or draw it. I can't even plot it in Mathematica for you. So just know that all that's going on here is that for every single thermodynamic quantity that you add onto an independent axis, that you get another Gaussian effectively. So straightforward generalization of what we were talking about previously. Now our definition for what equilibrium means is that it means the following. So we have first condition, that the change in entropy with respect to the energy is constant, or 0. We have the one that we just discussed. And UA, that is 0. Now what do we think we'll have? Now that we're letting let's say the number of particles change between the systems. They're able now to transfer particles amongst each other. Any thoughts for what this condition should be? So we've got U, we've got V. What's the other one we can let vary? Anybody? Number of particles? T? Not T. So T, the temperature corresponded to this one, right? The pressure corresponded to this one. This one will correspond to the chemical potential. But the thing that we let vary between these two, this one we allowed the systems to exchange energy. This one we allowed the systems to exchange volume. Now we're going to allow the systems to exchange particles. So like on the first or second day of class, we talked about basically the 3 different types of equilibrium that we're going to talk about in this course. And now we are finally fleshing out what all of them mean in terms of fundamental quantities like the entropy. So this is now what we mean by equilibrium. Okay. Don't actually have a lot of time and I don't want to rush this. So I think I might call it right here and we will finish up this little bit of chapter 3 next time. And then that should leave plenty of time for chapter 4 for like the next class and Friday. And then chapter 4 will basically be like a 1-day of class thing. It'll be very, very quick. We're just going to discuss like the maximum efficiency that engines and refrigerators can have and then call it. Okay, so if you have any questions about homework, exams, or anything, feel free to come to office hours right after this. And this entire lecture was recorded, so it will be uploaded shortly after lecture finishes today. Okay, does anybody have any questions before we let this go? Nope. Okay, well, I will let you go then, so you are free to leave. Thank you.